Hey guys, welcome back to my series on restoring classic late 40s American black and white electrostatic televisions. In this series I'm going to be pointing out some of the differences between these sets and the more common magnetically deflected sets, give you some tips, some tricks, some suggestions, some pitfalls to avoid to get these up and running. This is going to require some caffeine. Let's see if we can get through this. First off, let's go back to talking about the construction of an electrostatic CRT. Back here at the base end, we've got our electron gun, some accelerating, focusing elements, and there's some stuff right down in here that we can't see very well. Then we have all this gray coating on the inside. That gray coating is conductive. It's very similar to aquadag, the stuff that's on the outside, typically of magnetically deflected CRTs, that gets grounded. This internal coating is also conductive, and it's going to the highest potential, in this case, about, let's just round it up, and let's just say 6,000 volts for the rest of this discussion. So you have 6,000 volts on that, and right down in here we have deflection plates. Try to give you guys a peek at that. We can see the tail end of two of them right here, right before that graphite coating starts. There are two plates like that, and they're kind of angled outwards. And then right below that, there are two more angled this way. So we have two plates like that, two plates like that, a little bit of a gap between them. Those are 90 degrees apart from each other. So as a consequence of that physical construction, the ones that are further back, closer to the electron gun, are more sensitive because they get the first whack at deflecting those electrons. So imagine if you deflected a little bit here, we've got all that distance from there to the end for a little deflection here to build up and spread out more. But by the time you get closer to the front, you don't have as much distance, so you need to push a little bit harder. Well, the designers have a decision. One set of plates is going to be vertical, and one set is horizontal. Which is which? Well, one of them runs at a much higher frequency than the other. The vertical scanning frequency is much, much lower than the horizontal scanning frequency. So they choose to use the less sensitive plates for vertical deflection and the more sensitive plates for horizontal. Why? It's easier to build a higher voltage, low frequency amp than a high frequency, high voltage amp that maintains a really good linearity. So that's one design's decision that will play into something very important about that voltage divider string. Let's talk about that next. So there's a focusing element in that electron gun that needs to be, let's say, 2,000 volts. You have 6,000 volts coming out of our power supply, so we need a voltage divider. So let's just make a simple one. I'll put it over on this side. Let's say our input, and we have 6,000 volts. I realize we're going to need a lot of room vertically, so I rotated this board. Let's say we've got our 6,000 volts coming in the upper right. Now that goes to a bunch of resistors, and we have 1, 2, 3, 4, 5, 6, 7, 8. Essentially 9 of them. So let's cram that in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then, well, doesn't quite go to ground. Talk about that in a sec. It does go to ground, but via a tube. Okay, and if we do a little bit of simplifying here, we got 1, 2.2, 2.2, 2.2, 1, 2, 3, 4, another 2.2, a 1, a 2.5, 2.5, a 1, and actually two 4.7s in parallel. That shouldn't be connected there. And put those in parallel, that's what, 2.35. So let's just call it 2.2 altogether. So we're going to do the math in a bit because I'd mentioned about the voltage drop across these resistors. We're going to figure that out. And this guy is actually a potentiometer. That is the focus control. So this goes to that conductive coating on the picture tube, that highest voltage. And this goes to the focus element. Okay, well, that makes sense, right? We want the highest potential on that coating to rip all the electrons towards the screen, accelerate them for that, and we have this, we can vary this control to vary the voltage on the focusing element to get a nice sharp picture. Why do we need those capacitors? Alright, I've drawn in here a simplified diagram of the picture tube. We'll start at the bottom. We have a 6.3 volt filament. Above that, the cathode. That is where our video modulation is attached. The control grid is simply grounded. Other designs do it the other way around. They ground the cathode and modulate the grid. It really depends on the polarity of your video signal. When it reaches the picture tube, each amplification stage typically inverts at 180. So by the time you get here, it could be one way or the other way. Above that is our focusing element going to our potentiometer and this divider grid. Those slashed lines represent the deflection plates, horizontal and vertical. We'll have the horizontal here and the vertical here. The black line is the internal conductive coating, which is going to 6,000 volts. That yellow squiggle, that's the internal phosphor coating, and we watch the image coming out at the end of it. Alright, the capacitors, we have 5 of them. One of them is simply to filter the high voltage, so it's simply going from here to ground. Alright, what about the other 4? It has to do with the physical design and construction of this particular CRT. Where are those deflection plates? They're right inside the end of this conductive coating, which is at 6,000 volts. You need to feed a signal into these to move that electron beam around. Well, if you look up the specs, it'll say something like it takes 100 volts to move the beam an inch. And typically it'd be in the middle, so if you want to go 3.5 inches to either side, you're going to need plus or minus 350 volts. It's driven by push-pull tubes, so you need 0 to 350 on either side to move it one way or the other way. But those plates are physically close to 6,000 volts. Say you've got 100 volts on here, 6,000 there, it can jump that gap internally and short out. That's a problem, obviously. So how can you address it? You put these plates at around 6,000 volts and you capacitively couple your modulation into them. So if you look at the schematic, I left this out. I simplified this. This isn't actually a 1 meg resistor. It in reality is, there. Get rid of this cap. Just remember it's there for filtering. A little bit more room here. There are actually 2 potentiometers here that are each 2 meg, so in parallel it's 1 meg. This goes to the deflection plates, and the other side goes to the other set. There are actually some more resistors in here. I'm oversimplifying things a little bit. Those are your centering controls. You vary the bias on these plates to get this manufacturing and all that is 100% perfect, and you adjust those to move the beam around a little bit. But basically these are at the same potential as that graphite coating, and then we capacitively couple our modulation signals in from our amp. So DC bias provided by some pots right off the 6,000 volt line, and then we capacitively couple our signals in. So on these caps we got about 6,000 volts on one side, but the other side can be, say, 0 to 350 volts, and they will combine on the other side of the cap and everybody's happy. Now there are early oscilloscopes that also do this trick. But there's a problem if you wanted to, say, do an oscilloscope and you put in a very low frequency, your DC, well, that would get blocked or severely attenuated by these caps. So another way to do this is you ground this conductive coating, you get rid of the caps, you put DC to 350, 0 to 350 volts or so on those plates, and you put minus 6,000 volts on this grid or this cathode. You flip it around. They could have done that with the TVs too, but typically this is what you're going to see. You have the cathode end grounded, and you put this at 6,000 volts. Now there are CRTs, typically smaller ones, that only run on maybe 1,000 volts or 1,500. You don't have this shorting risk, and you can do it. You have a lot more flexibility with the design, but that's why they did this. Now let's talk about this divider and down into here. So I mentioned that these vertical plates being further towards the front, or closer to the front rather, are less sensitive. So maybe we need 0 to 250 on these to get a full screen deflection. But maybe we need 0 to 400 on these to get a full vertical deflection. Well, remember, our power supply is pretty simple on this set. We just have a single 5Y3 rectifier and B plus coming out here. Say it's 250 volts DC running the whole set. How are we going to get 0 to 400 volts if our B plus is only 250 volts? We can't create more voltage out of thin air, or can we? So the 6SL7 vertical output tube plate voltage doesn't come from B+. It doesn't come from the main supply of the set. It comes from this. So we divide 6,000 volts through all these resistors, and we get down here and we're down to around 500-600 volts, and these two 4.7 mega resistors are our plate load resistors. So this tube, this one tube, is running on much higher voltage than the other sets, which is very much akin to what magnetically deflected sets do for the boost voltage for the vertical circuit for a similar reason. But in those sets, you've got a flyback transformer and a damper circuit, and you can steal voltage out of that to get 400, 500, 600 volts for a similar need in magnetically deflected sets where you need a bit more oomph to do the vertical deflection. We need it here too, but we get it in a different way. And that's why these resistor values are so important. It's not just for the focus, it eventually feeds this. And if these have drifted all over the place or deteriorated, your plate voltages here could be wrong, and they could also not be equal to each other. It might not be symmetrical. So one common problem I've seen is that your centering control can't center the picture. And that's typically because these resistors are no longer equal, and you've got more on one than the other, and these work in a push-pull manner. So the output of these plates goes right to these capacitors. So these go right over here. So say one is drifted up to 5.6 and the other one is maybe drifted down to 3.5 or something. Your image is going to be shoved to the bottom or to the top, and the little bit of tweaking you can do on the centering control isn't going to be enough to compensate for it. That's one of the reasons I just go ahead and replace all these, is they are important. And likewise, if these are off, or your tube is weak, or if something isn't perfect in this, the voltage range for your focus control is going to be off, and you won't be able to get a sharp focus on the screen. I removed the CRT and went back to my simplified voltage divider here with 1 mega top and 2.35 at the bottom. Let's do a little math and try to figure out the voltages at the various points. Now there's one unknown on here. This goes to ground at the bottom, of the cathode's down there, but what is the voltage at this point? Now that's 6SL7. I exaggerated a bit to hammer home the point. I looked at the Sam's Photo Factor, which gives the plate voltage for the 6SL7s, and they have it at 210 volts there. So that's all we need to know. We know voltage from here to there, so let's just call it 5,800 volts across this. And we got all those resistors. So let's add up all the resistor values, and then we can divide voltage by resistance and get the current. Then we can find the drop across each resistor. So let me whip out a calculator here on my phone, and let's see if I can do this without making any mistakes. We are 1 plus 2.2 plus 2.2 plus 2.2 plus 2.2 plus 1 plus 2.5 plus 1 plus 2.35 equals 16.65. I'm going to call that 17. So we got 17 mega ohms across this whole thing. So let's do our Ohm's law and do 5,800. Now let's leave it at 6,000. Let's just round everything off. So we've got 6,000 over 17 mega ohms. What does that come out to? 6,000 divided by 17 million is 350 microamps. Going through all that. So let's just call it 0.35 milliamps is another way to say that. So if we want to know the voltage drop across all these, actually if we keep these in megohms and this in microamps, we can just use the values as they are. So voltage is current times resistance, right? So the first one will have 350 volts across it. That's easy. We got a better marker than that. That one's a little fuzzy. Let's try this guy. Alright, and then 2.2 times 350, 770. Remember I was talking about the voltage rating on these resistors? And how a 1 watt resistor has a voltage rating of 500 volts? How much do we have across that resistor? 770. And even if it was a 2 watt resistor, which is a rating of 750, we're still exceeding it by a little bit. Now those resistors are, sometimes it can be a little hard to judge the wattage going by the size. Those might be 2 watt resistors. It might just be a little bit different package style. So I'd have to consult the service info parts list, the original Admiral parts. If you go to the early television website, they do have the Riders Volume 3 contains this chassis, which is a reprint of the original Admiral service info, and I haven't looked, but that might have a parts list that actually lists the wattage rating on it. But anyways, we can continue. And 2.5 times 3, oh, yeah. Times 350. 875. If you needed to replace one of these controls, that's something to consider too, is that you're going to have a bit of voltage across that. 350, and then finally 350 times 2.35 is 822. Should be a 7. So there you go. That's why those resistors are so important, and that's why I highly recommend you use the VR37s. Or get yourself some 3-watt resistors, although I don't think those have any higher voltage rating. You know what? No, forget that. Just go with the VR37s. And I looked up. I found a data sheet for carbon comp resistors. And yeah, 2-watt, 750. However, they do mention a surge rating, which is about double that. But for a surge or a spike, they're talking like 2 seconds. That's one of the reasons carbon comps are still made, but pretty hard to find, is they can handle a voltage spike easily 2-3 times what their typical voltage rating is and be fine. Metal film blow open. So that's why they were around for so long, and that's why they are still using some niche applications. They can handle voltage spikes. Those metal film, it's vacuum deposited metal on a ceramic cord, and they spiral cut it to trim the exact value. Well, where that's, imagine it's like a spiral of thin metal on a ceramic core. You get a voltage spike, it just blows open like a fuse. So inherently, most metal film resistors are fusible resistors. They will safely go open if the ratings are exceeded. Not always so nice depending on your application. But anyways, I figure if we go with resistors that are good for 3,500 volts, even if there is a spike on this, it's not going to be that high and you'll be fine. But that is what I was getting at. There's the math, there's the numbers. That's why I suggest you replace these with VR37s or equivalent. Oh, and if any of you want to double check my work and you add all these numbers up, including the 210, no, it doesn't equal 6,000. It's a little bit less. Why? Because it's actually a little bit higher than 350 microamps. I rounded it down a little bit to simplify the math. So it's actually going to be even a little bit more than 770 across these resistors. Hey, why don't we just take a look at that original Admiral service info. It's available at earlytelevision.org. Go to their main page, go to post-war TV, technical information. They have it broken down by manufacturers. They also have the original service info for Motorola VT71. Both of them are fantastic reads, whether you're going to work on one of these sets or not, if you're interested in the technology, how the circuits work, because they are both extremely well written and very detailed. It's 32 pages of info, a lot more than you're going to get in the SAM. So here's the first page. You start out with some specs, tube lineup, tube chart, warnings about the high voltage, and then controls and how the basic operation of the controls, installing it, setting up the antenna, getting the picture looking the best, info on how to replace the picture tube, and then we get into the circuit discussion, which is, again, is excellent. You break it down, block diagrams, all the stuff we've been talking about. They go through every circuit and give you a detailed explanation of what it is and how it works. The whole info on the tuner. They even break it down, show you about those strips that can come out and various components inside. I highly recommend you never open one up unless you have a very, very good reason to. Very easy to mess them up. Now we get into the alignment instructions, which again are very extensive. And then this is great. Waveform analysis. Most service techs didn't have scopes back then, so I was surprised they go into so much detail with all these test points and photos of what the waveform looks like. You notice in a lot of areas there's both. A lot of early scopes that were designed for TV servicing often had a setting for vertical and for horizontal, rather than time-based broken down into microseconds and milliseconds. So this is the shot with the scope in the vertical sweep rate position, and this is with the scope in the horizontal sweep rate position. So that's what you should see if things are working right, and on and on and on. So there's our sawtooth. And nice and clean that is. But by the time you get to the plate of the vertical, or sorry, rather the grid of the vertical output tube, it's not perfect. Again, these are budget sets, so they did the best they could. I don't think, they do. Plate of the vertical output tube, so it's 286 volts peak to peak on those plates, which is odd, 'cause that's a little bit higher than the plate voltage that Sam's listed, but I would trust this more than the Sam's. I'm surprised though that it's a bit mushed off at the top there, but maybe that's during the vertical retrace interval, so it's not that big a deal, and that's the visible area, but even so, it's not exactly perfectly linear. And then troubleshooting, and all sorts of tips about that. Production changes. There aren't too many, I don't think. And now we get to the parts list. This is what I wanted to see, the parts list. So here are those 2.2 mega ohm divider resistors. They are 1 watt. And they got 770 plus volts across them. That's not good. I imagine back then the parts were made with a little bit looser with specs, so even if they were rated for 500, you could go over that and they'd still be fine. But as the decades roll by, I don't think they can handle it quite as well. And it just goes on and on and on and on and on. Just a wealth of information. Now we got a whole troubleshooting section. If there's your problem, that's what you should check, and then there's some notes. And we may be referring to this if we need to. And on and on and on. And finally we get a schematic, which is exactly the same as what Wallace reprinted. But it's all in one big sheet rather than broken up. That's why I like to use them. And that's the end. Now let's take a brief look at the Motorola. They have one for both the TS4 type and the TS18, which are similar, but the TS4 is the one that's really impressive. It's 107 pages long. If you want to take a master course on electrostatic television design and operation, read this. Now, to be fair, part of the reason it's so long is there are 7 or 8 chassis variations. They include schematics for all of them at the end, so that takes up a lot of it. Starts out in the same way with block diagrams and basic operation, how to set it up. But they have some cool diagrams like this where they break down the power supply and how the various tubes are there and interact with each other. And same type of deal. Break down each section to give you theory of operation. Here's the IF amplifiers, for example, showing the bandwidth and frequency response curves. There's the AGC circuit. There's a detector and video amp with that early germanium diode detector in there, and on and on and on. And this is a big part of the reason why I know what I know. Some of it's from experience of working on them, but the other is from reading all of this. So there's your homework assignment. Read the 19A1 factory service info and the Motorola VT71 factory service info.